Welcome everybody, I'm Mr. Ullman, and today we're going to be running through some review for the final assessment for this unit. So we're just going to hop right into it. The first question we've got here is, we have a bunch of fractions. We want to reduce the fractions if possible. If possible. So we may or may not be able to do this. Let's start off right away by seeing what's happening with this first question. 39/6. 39/6, beautiful fraction. The way we approach reducing a fraction is we think about the common factors between the numerator and the denominator. Are there any common factors? Well, let's figure out what the factors of 39 are. We can think about this in terms of prime factors if we want as well. We're going to get into some prime factoring in just a few minutes. So 39, just by looking at it, it doesn't look like it's divisible by 2 because it's not even. It doesn't end in an even number. Is it divisible by 3? Anybody remember what the rule for divisibility is, the property for the number 3? If the sum of the digits of your number are divisible by 3, then the number itself is divisible by 3. So 3 plus 9 together is 12. 12 divided by 3 is 4. And so since 12 divided by 3 works out to 4 cleanly, and we get an integer, a whole number, we know then that 39 is also divisible by 3. So we know that if we divide 39 by 3, we're going to get 13. So we can think about 39 as being the same thing as 13 times 3. We haven't actually canceled anything out yet, but we're showing what the factors of 39 are. And we're done here because 13 is prime, as is 3. So now let's figure out what's happening in the denominator. 6 is maybe a little bit easier for us. 6 is an even number, so we know it has a factor of 2 in it. And what number do we multiply by 2 to get 6? Well, it's our good friend 3. Now this is nice. What we notice here right away, or we hopefully can notice after a quick glance, is that we have a factor of 3 in the numerator and the denominator of our function. And that means that we can cancel out those factors. I said in our function, I meant in our fraction. Moving forward, we can rewrite this fraction as 13/2. And since both of these numbers are prime, they are going to have no common factors. They cannot be further reduced, and so we're done. Let's take a look at the next question, going through a little bit more quickly this time. 35 divided by 15. This one's nice. Thinking about rules of divisibility, I should have alarm bells ringing in my head when I see numbers ending in 5, because if a number ends in 5, it is divisible by 5. So let's write out 35 and 15 each as a product of their factors. I know that 5 is going to go into 35, and I can divide 35 by its factor, 5, to figure out what we would have to multiply by. So 35 divided by 5 is 7. We know that 5 times 7 is going to give us 35. And what about 15? Again, maybe a little bit easier here. Smaller number in the denominator. We know that there's a factor of 5 because the number ends in a 5. And 5 times 3 is 15. So we can notice, once again, the common factors of 5 and 5 in the numerator. We can cancel them out like we did with the 3's in example A, and we can proceed forward to rewrite our reduced fraction. And look at this. What do we notice about 7 and 3? That's right, 7 and 3 are both prime numbers. And once again, they will not have any common factors, and we're done. You might be wondering, does your fraction always have to be made up of primes at the end? And the answer is actually no, but we're not going to get into exactly why that is right now. If anybody's curious, feel free to ask me in class next time we meet after our evaluation. Example C, we're going to blast through this one even more quickly. 29 let's see, it's not even, it's not divisible by 2. If you add its digits, 9 plus 2, you get 11, and that is not divisible by 3. So it's not divisible by 3 either. Or 4, because it's not even. It doesn't end in a 5, not divisible by 5. Does 6 go into 29? Well, I know that 6 goes into 24. I know my times tables. And I only need to go 5 more away from 24 to get to 29. And 5 is not divisible by 6. Only 24 is. So if this is divisible by 6, but this isn't, then we know that our total answer will not. Our 29 is not divisible by 6. And we don't need to check any more factors than that. Once again, I'll explain exactly why that is in our next class. But usually if you check up to about 6, you're pretty good to go. So 29 cannot be reduced here. And 7 is already prime. So we actually can't reduce this at all. We just end up with the same fraction we started with. So we'll give a big tick and we'll make a quick note to ourselves that it was irreducible right from the get-go. Okay, let's move on. Next question. Let us find the prime factorization of the following numbers. So we already hinted at prime factorization in the first example. We took 39 and we split it into 3 times 13. That was a prime factorization. So here, in example 8, we've got 450. Let us create a factor tree, shall we? We'll start with 450 at the top. This is how we learn to do it, channeling our inner Eratosthenes here. And we can immediately start checking primes. Is 450 divisible by 2? Well, it ends in a 0. We consider 0 to be part of the evens. And so, in fact, it is. 2 is a factor of 450. We can divide 450 by 2 to get what remains. And what are we left with? 225. Okay. Now, 2 is finished. We can't do anything else with that. That is prime. So we can see what the factors of 225 are. Well, it ends in a 5, so I know that 5 has to be in there. It's okay. I can cheat a little bit here. I don't have to go to 3 directly if I know that there's a factor that I can see immediately. So I can take 225 divided by 5, and I get 45. 5 is prime, so we're done with that branch, and we can keep going. 45. It ends in 5 again. Let's divide by 5. We know there's another factor of 5 here. And that multiplies by 9 in order to give us 45. We're running out of space. But 9 here can be split into 3 times 3. We should be familiar with this breakdown. And those are both prime as well. So we found the prime factorization. We'll write it down right here, the prime factorization. We have 1 copy of 2, 2 copies of 3, and 2 copies of 5. So 2 times 3 times 3 times 5 times 5. We can write this using exponents as follows. 2 times 3 squared times 5 squared. The squared tells us there's 2 copies of 3 and 2 copies of 5 in the product. So 2 times 3 squared times 5 squared is 450. Okay. On to 168. Let's do the same thing. Maybe try and space ourselves out a little bit more, expecting the left branches to cut out early. 168, that is even. We know 2 is a factor, it's prime, circle it, and move forward. What is left after we divide 168 by 2? We're left with 84. Just to really remind you here what's going on, it's 2 times 84 that gives us 168. So we know that 2 and 84 are factors of 168. Let's keep splitting up 84. We've got another even number here. So we'll take a factor of 2 out, and then we'll be left with 42. We're still even, so we'll take another factor of 2 out, and we'll be left with 21. We're no longer even, but we might recognize 21 as the product of 2 of our favorite numbers that both happen to be prime, 3 and 7. And once again, we're done. We have all the primes down the tree, and we can get the entire prime factorization. PF is 3 copies of 2, and 1 copy of 3, and 1 copy of 7. Let's make room for all of it right here. And we can use exponents once again. We have 3 copies of 2, so 2 will be cubed. It's going to have an exponent of 3. Then we can multiply by 3, because we've got 1 copy of 3, and 7 for the copy of 7. Alrighty. Moving on, that's prime factorization. The last few examples here, we're going to determine whether the following fractions are equivalent. It's one of the most recent things we learned about in our class. So let's take it one example at a time. We've got example A here. We're comparing 2 fractions, 16 over 11 and 64 over 14. We're looking at this one right now. The first thing we can do is we can figure out whether any of these fractions is reducible. If we compare irreducible fractions, this will allow us to figure out definitively 100% whether they are in fact equivalent. Otherwise, it can be hard to tell. So looking at 16 over 11, we can see that 11 is prime. So if 11 is prime, then we need to see, is 16 a multiple of 11? Well, 16 is not a multiple of 11. And so there are going to be no common factors between 16 and 11. So 16 over 11 is irreducible. We can write 16 as 2 times 2 times 2 times 2 if we really wanted. That would be the prime factorization. But 11 is prime. And none of the stuff in the numerator here is found in the denominator if you write out those prime factorizations. So there is nothing to be canceled. Here, 16 over 11 is irreducible. What about 64 over 44? Well, these are both even, okay? This is something I want you to think about when you're thinking about reducibility. If you've got 2 even numbers, they both have a common factor of, they're both divisible by 2. So we know that we've got 16 over 11, and, well, 64 is something times 2. It's 32 times 2. And 44 is something times 2. It's 22 times 2. So we find common factors of 2. We can cancel them out. And what we're left with is 32 over 22. Okay. We haven't reduced fully yet, though, because 32 and 22 are still both even. This is not always going to be the case, but we might always still have to find more common factors. Once again, let's write this. 32 over 22. We'll come down here, get a little more space. 32 is even. We've got a factor of 2 times what's left? 16. We've also got 22, which is 2 times what's left? 11. Ooh. If you got the chills right there, that's very, very good, because we can see now that our 2's will cancel. And look what we have here. 16 over 11 remaining. So what can we say? Well, we can say that the following are equivalent. 16 and 11, I'm pretty sure, you might have to double check me on this. Pretty sure 16 over 11 is equivalent to 16 over 11. I'm not wearing my glasses though. Okay, so let's demarcate this for us, get a little more space, going for example B. A couple more and the video is over. You can continue with your independent study. Think about the lovely things that you've learned in this video. Take a few notes and takeaways. And of course, if you have any more questions, we can review that in our next class. Okay, so 12 over 60 and 36 over 183. I'm a little bit nervous about that second fraction. I see some big numbers. Might want to deal with that afterwards. Let's look at 12 over 60 first. As we always do, we want to reduce, reduce, reduce. Common factors, here we come. 12. Let's write out the prime factorization of 12, shall we? 12 is 3. I know there's a factor of 3 in there, and there's 2 factors of 2. If you need a review or refresher for that, go to the previous set of examples here, rewind about 5 minutes, and look at the prime factorization examples. 60, it's even. We've got a factor of 2. After we divide 60 by 2, we're left with 30. That's also even. Pull out another factor of 2. Then we're left with 15. And we already divided 15 before in the first set of questions. We know that that's 3 times 5. So look at that. That's a 5 there, folks. That's not a great 5. So 3 times 2 times 2 is 12. 2 times 2 times 3 times 5 is 60. And we've got lots of common factors. We've got a 3 in the top and a 3 on the bottom. We've got a 2 on the top and a 2 on the bottom. And we've got another 2 on top and bottom. And you know what happens to those? Gone. So what are we left with? Well, this is where mistakes often happen. We see that there's no more factors left on the top, so we think, oh, must be 0. But we must remember that 1 is always a factor of every number. So when in doubt, put a times 1 there. We're not left with 0 because we're dividing out all of these factors. And we're left with a factor of 1 that remains. So look at that. 1 over 5 is the reduced form of 12 over 60. Now, can we get 1 over 5 from 36 over 183? Well, there's a long way and a short way to do this. I want you to try and do the long way on your own, but I'm going to show you the short way because I know that's what you really want. Let's think about this, okay? Really critical thinking here. We're not just going to waste time going through things willy-nilly. We're going to look at the denominator here, 183. Let's do that in red, really draw our attention to it. If we're going to reduce this fraction, 36 over 183, to be 1 over 5, so that we can see if it's equivalent, that means we have to have a factor of 5 remaining in our denominator when we're finished. But folks, 183, I hope you can recognize, based on our rules of divisibility, properties of divisibility, 5 does not go into 183 because it does not end in a 0 or a 5. And so immediately, without any further work, we can say no. These, in fact, are not equivalent. How satisfying is that? It's important to recognize that mathematicians, which is what you all are and working towards becoming, they're a little lazy sometimes. So it's okay to take that shortcut as long as it comes from deep analytical mathematical thinking. Okay. Like I said, I want you to try and go through that on your own the long way and prove to yourself that it is in fact a set or a pair of not equivalent fractions. And here we're going to end on a nice note. This might look either very simple or very confusing. Example C, 100 over 100 and 61 over 61. You'd be amazed how elusive these fractions can be, and also how helpful they can become later on in math. This is just grade 7, so we're getting started in our high school careers. 100 over 100, does anybody know what this is? Well, this is a fraction of the form a over a. And what I mean by that is it's a fraction where the numerator is the same as the denominator. These are the same. And if you take a number and divide it by itself, you can have fun with your calculators and do it. Take 8 divided by 8, see what you get. Take 20 divided by 20. Take 3 divided by 3. Every time you do it, you're going to be getting the number 1. I don't want you to forget this. This is not just helpful for this test or for this unit or for this grade. This will help you for the rest of your mathematical career. A number divided by itself is equal to 1. So right away, we should be able to say if 100 over 100 is a over a, that's 1. 61 over 61, those numbers are the same. They must also be 1, and so these are equivalent. Now, why is this the case? It's the last thing I'll say, and then we're finished for the day. When we do division, 100 divided by 100, we're always asking the question, how many times does the denominator go into the numerator? I'll write it down visually so you can read it. How many times does the denominator go into the numerator? Well, I hope we can see at this point that 100 goes into 100 all of one time. And so when we write the reduced fraction, when we think about the value of this fraction is equal to 1. The nicest one you've ever seen. And that's our time. Thank you for joining me.